Yes, you can speak.
Yeah, thank you. Hello everyone. I'm going to present you the work titled Model-Based Design and Analysis of an Adaptive Exoskeleton Globe for Remote Rehabilitation, Integrating Computer Vision and Flexor Actuation Systems, right? For this, this is the agenda, and let's start. First of all, I'm going to talk about a little bit more, not from the technical point of view, but from the issue, the social issue, right? First of all, the medical care management challenges are rising due to the rising also in the chronic diseases and in population growth, right? So, in the Latin American context, there's more issues for this, because in Latin America countries, we face the issues of the costs, the geographic barriers, and inadequate government investment, right? So there are many issues that the population faces in order to have a medical attention. So for this, one trend that is rising is the e-health. And for this, we are focusing on rehabilitation, right? So to rehabilitate with an exoskeleton, you must be focusing on the joint injuries that a person may have, right? Certainly on one limb or several limbs of the body. And for this, we are trying to connect the exoskeletons with e-health, right? But also we need normally therapists. So in Latin America, another issue is the cost of a specialized therapist, we could say it. And with this, let's say, solution, we are aiming to help reduce those costs and also the geographical barriers, right? Well, now for the state of the art, we are focusing mainly in subsystems and the feedback developments, right? There are some other works that use the soft approach of exoskeletons to help in the rehabilitation process, and also in the feedback to help the rehabilitation in other ways, such as a better design using motion capture or the video-based rehabilitation, right, via the Kinect sensor. Well, for this, we made this methodology that we use to design an exoskeleton, a globe exoskeleton. First of all, the first stage is the movement recognition. We need the movement recognition to know what is happening with the person, or what is the therapist guiding to do for the patient, right? So after that, we need to try several actuators in a way that those actuators are the best solution for that patient, for instance. Then it's to design and simulate the exoskeleton. Here I made a comment. It should be also added to to develop the prototype of the exoskeleton, not only simulate it, because at least for this work, we work with undergrad students, so they are now engineers, and at that time there was the pandemic, at least in Mexico, so we couldn't do or develop the prototype, right? And finally, the integration with models, which is aimed for the e-health part, right? So the case study we developed, it's the exoskeleton D2XP. That's the name the undergrad students chose, right? In the first stage is the movement recognition. For the movement recognition, we need to select a sensor. In this case, we use the cameras, and specifically the web cameras of the computers. So we extract this information, and thanks with Python and OpenCV, we extract, we process and segment the information, so we can use it later for extract the certain characteristics of the images, and then classify a gesture using the hard cascades and several other filters, right? So whenever we are using our hands, the algorithm will detect, will recognize which gesture we are doing at that time, right? And for this, we got help from therapists by looking for which gestures are the most common used on hand rehabilitation. And on the top one, on the top figure, what is happening is there's the repertoire of the detectable gestures normally the therapist use in order to rehabilitate a person, at least with the hand, right? So in the bottom picture or figure, what is happening is the classification using the algorithm, right? So we only specify the region of interest in, if you can see on the green square, to help the processing, right? And whenever the gesture is doing, the algorithm is classifying it. Well, then we need this next stage is the choose, evaluate, and simulate the actuator system. So for this, we need to first choose the actuator system, and I want to emphasize the part that normally we need user-friendly mechanisms to be used with patients. If the patient is having troubles with an exoskeleton, or not only an exoskeleton, with any other system, the patient won't use the system even if it's helping them, right? So that is the approach, and we use a mechanism inspired by the Hill model, the Hill biomechanical model, that is saying that there should have an elastic element and a contractile element, right? And for this, we selected the twisted string actuator system, the TSAS, which incorporates these parts, right? These elements. And this is the TSAS, right? The video of how it is being used. In summary, the TSAS has two ropes, and with those ropes, you are twisting the rope. And whenever you're twisting that rope, what you are doing is shorten the distance of those ropes. So that is the movement. We change the rotational movement into linear movement. Well, and for that, we could select two models, the kinetostatic model that is telling us about the relationship between the twisting angle of the rope and the force that is being applied to those ropes, right? Because there are several forces, and there can be any external force to that rope, and we can use this model, the kinetostatic model, and also the non-linearity compensation model, which is assuming that whenever we have the two ropes, the space occupied by the twisted string, whenever it is being twisted, the shaft decreases by half. It said that with each rotation, the decreasement will be by half. However, this is not true. It decreased, but only partial, right? So, however, this model has a better accuracy than the other model. However, the issue here is that we are aiming for a low-cost solution. So, it has a better accuracy, but we need a higher computational process to do this, right? So, we stayed with the kinetostatic model, and for this we evaluated because this was only made by digital means, and this is the evaluation. We chose what is the average cylindrical palmar strength of normally the grip of the person. This is only an average, and we found that it was the 21.7 kilograms force, and with that we calculate the force in each of the fingers, and assuming some of the parameters for the design exoskeleton, we selected the rope length and the rope radius, and with that we see that the model is nonlinear with the first figure, and in the second figure we did a simulation, a finite element method simulation of the two ropes twisting between each one, and with 4 rotations, and in the paper is with 10 rotations, right? Assuming the ropes are made from Kevlar, right? Due to the mechanical properties the Kevlar has. So for the evaluation and simulation, we got the graphs for the string deformation and the string stiffness, saying by due to the mechanical properties of the Kevlar, after some twisted for some rotations, the formation and the stiffness remains constant, right? So using this information and with a proposed DC motor, we got the dynamic behavior of that motor in each of the fingers, right? So based on the torque that the motor should be doing during the period of the therapy, right? And then we only do the design of the exoskeleton in a CAD software, and after that what we wanted to do is to show how this actuator can be used in the exoskeleton, right? So we export this CAD into Blender to add any texture, and after that we export it to Unity to add the armatures in Unity, so we can simulate the movement, the proper movement of the phalanges of the hand, right? So because this was not made physically, this was the approach, right? And after that we perform the library of all the animations of the gestures the therapist recommend us. And finally, what we are using in the last stage is we import all the animations from Unity, and we connect it to a UDP server, and after that we execute the interface. In the interface, let's say we can imagine that the therapist is connected through the interface with the patient, and the therapist is guiding the patient doing the movements he or she must be doing at that time, and with Unity these simulations are happening at the same time, right? And this is the final part, the evaluation of all the integration process of the methodology. We are seeing that depending on the person, the gesture the person is doing at that time, the person is doing at that time, the animation is changing according to the same recognition, right? And for conclusions and future work, the study introduced a methodology for creating an exoskeleton globe. This exoskeleton globe was based on the heel model, and also, and we select the twisted string actuator system. We simulate this approach in order to know if it can be a suitable option for this exoskeleton, and for the future work we are aiming to make a prototype, a physical prototype of this exoskeleton, and approach it with several populations of Latin America if it can help on the rehabilitation process, right? Also to implement a control system and incorporate machine learning to have an improved gesture recognition, right? And that's everything for my part.
Okay, thank you very much.